In this lesson, we want to introduce a framework that can handle deviations from the standard Petrov-Galerkin setting. This framework is usually called the variational crimes framework, and such crimes actually quite naturally arise in practice. So before introducing the rigorous setting, let's look at some examples. The first natural example is numerical quadrature. So let's look at this example where we have a Poisson equation with variable coefficient a. Here, of course, bilinear form a, and this ax is just a coefficient function. Let's say some smooth function. And the right-hand side is, of course, f integrated against the test function v. And in practice, to compute the stiffness matrix and the right-hand side vector of the discrete system, we will need numerical quadrature, because this integral may not be computable analytically, or even this integral here. So we will need to replace the integrals by numerical quadrature, meaning that instead of the integral we get this sum, or with some weights omega I and with quadrature nodes xi. So we may apply different quadrature to the right hand side, or you may apply the same quadrature. And you can see that by doing this we actually change the bilinear form A by some other bilinear form AH, where AH is defined only for functions from the finite element space. Because in general, for example, in this setting, the energy space will be H1, and for H1 functions, you cannot evaluate these functions pointwise. But for finite element functions, in general, let's say we have piecewise affine functions, evaluating these functions pointwise is no problem. And it has also the effect of replacing the right-hand side f by some right-hand side fh that is defined only for finite element test functions. And after applying the theory, we will see that the typical assumption we will need will be that the approximate bilinear form AH, which has the quadrature in it, should be close to the exact bilinear form, and the approximate right-hand side should be close to the exact right-hand side, which are natural, and we also need the approximate bilinear form to be insubstable in the finite element space. So these are the conditions that we need typically. The next example is isoparametric elements. In practice, we need to handle domains with curved boundaries or even PDEs defined on curved surfaces. One way to handle such situations would be to have straight triangles here in the computational domain, and then we map those straight triangles into curved triangles by some mapping phi h, and this phi h is going to be piecewise smooth, so it will be smooth in each triangle. Now once we have this mapping phi h, one way would be, of course, just to define the approximation space or the finite element spaces xh on these curved triangles as the image of the finite element space on the straight or reference triangles under this mapping. Then we just form the stiffness matrix and everything on this domain with this approximation of finite element spaces, and we can do everything as before. In that case, this is not going to be a variational crime. What we need is an approximation theory on these curved triangles. So, for example, the finite element spaces are not going to be polynomials anymore, unless, of course, this phi h is a polynomial itself, and we need some theory to take that into account. Now, the second way would be look at the triangles here, this domain omega hat, and look at the pullback of functions on the curved triangles under this mapping. So this u hat, for example, will be a function defined on these straight triangles. Then what we do is we simply take the bilinear form on these straight triangles as an approximation to the bilinear form on the curved triangles. So we can write this bilinear form AH in terms of quantities on the curved triangles or the real domain omega, and if you write it, you will pick up some Jacobians of this mapping phi h and also the determinant of the Jacobian of the inverse mapping. We want this AH to be close to the original bilinear form, which would be AUV equal to the integral over omega nabla u dot nabla v. And for that, it turns out that simply we need to assume that the Jacobian of the mapping should be close to the identity. So in other words, what we need is this straight triangle. Let's say that we can draw that triangle here. This straight triangle and the curved triangle should be close to each other. And we can imagine that as we refine the mesh, actually this triangle is getting closer and closer. So for example, in the next iteration, we will going to get such a small triangle, and this small triangle with straight edge is close to the small triangle with the curved edge compared to the bigger triangle with the straight edge. We can also combine these two approaches. Instead of approximating these curved triangles by straight edged triangles, we can approximate them by triangles with edges that are described by polynomials. Then that polynomial triangle is going to be close to this general curved triangle. So that way we can actually apply both of these approaches at the same time. The next example is some other ways to deal with curved boundaries. We consider just the Poisson equation with homogeneous Dirichlet boundary condition. The first approach would be a simple interpolation. The omega is this triangle with curved edge. And we want to have, of course, zero boundary condition on this curved edge. But in this approach, what we do is we simply take, for example, for us, one of the elements would be this triangle with curved edge. But we simply take finite element space, which is affine in this triangle, and zero on that green edge. So our finite element space is going to be piecewise affine and zero at the green and black edges. So zero here, zero there, and zero on the black. As drawn in this picture, everything will be zero if we require the function to be zero over here, but we are thinking of more refined triangles, smaller triangles, and so on. So one deviation from the standard framework here is that this finite element space is no longer in H10 because it does not satisfy the zero boundary condition on the curved edge here. It's only is zero along this green straight edge. So our finite element space is no longer in the energy space H10. But of course, our finite element space is more generally in H1 without the boundary condition. And there is no problem to define this bilinear form on this finite element space without zero boundary condition on the curved edge. But you can see that as the triangles become smaller and smaller, for example, in the next iteration, we're going to get such a triangle, and the functions in the finite element space will be zero on that edge, which is very close to the curved edge. So that's the intuitive reason why this method works. And what we need is that this bilinear form is substable in the finite element space, which is finite element space with zero boundary condition over here. And more generally, of course, we can have higher order finite element spaces, and your boundary condition is going to be not zero on a straight line. For example, for the quadratic case, you can take finite element functions which are zero on these two and also zero on that one point on the curved edge, and so on. The second approach we consider is called boundary penalty method of Nietzsche. Here what we do is we simply take the finite element space to be a piecewise affine space without any boundary condition, and we're going to actually impose the boundary condition through the bilinear form. So the bilinear form is modified in this way: some term on the boundary and some penalty term here. It will turn out that actually it works and it will enforce the boundary condition, even though not exactly. Again, we will typically need this bilinear form AH to be substable in the finite element space. In the fourth example, we will look at non-conforming discretizations. So non-conforming discretization usually means that the finite element spaces are not in the energy space. So in some sense, this is a natural extension of the Nietzsche's method and the other method to treat the boundary conditions. For the boundary conditions, we had some nonconformity at the boundary where the finite element space is not in the energy space because there is some modification at the boundary. Now, for non-conforming discretizations, we actually have modifications over all the edges. In this particular example, let's say we take our finite element space to be discontinuous piecewise affine functions in each triangle, which have continuity constraints at the midpoints of the edges. So in this particular example, we're going to get, say, zero boundary condition, then we're going to enforce zero data at those midpoints, and then we're going to enforce continuity across these 2 points. So the value of the affine function over here and value of the affine function over here will be only required to agree at this point only. So there is going to be discontinuity at other places in general. So obviously the finite element space is not even in H1. For the Nietzsche method, for example, the finite element space was at least in H1, but in this case now not even in H1 because there is discontinuity. And because there is discontinuity, we will be required to modify our bilinear form in this way, which is of course consistent because if these functions u and v are in H1, then this sum will be just integral over the whole domain, and that would give us the original bilinear form A. Again, typically we will need that this modified bilinear form AH is stable in the finite element space. So actually it turns out that if you have these continuity requirements at the midpoints, we will really have IMSUP stability. So this is a type of non-conforming discretization. There are other types of non-conforming discretizations where you don't even require conditions such as continuity across the midpoints of the edges and try to impose these continuity requirements through the bilinear form itself, similar to Nietzsche's method. So these are usually called interior penalty methods instead of boundary penalty methods. And these actually fall into the category of discontinuous Galerkin methods. So one example would be you take discontinuous piecewise affine functions with no restrictions at all, and we simply modify our bilinear form by some terms which are similar to the terms that we used in the Nietzsche's method, except that these terms are now defined over all the edges. And this also will work. Now that we have seen some important motivating examples of variational crimes, it is time to introduce the abstract framework. And this framework is usually expressed through 2 lemmas called Strang's 2 lemmas that are generalizations of the usual Sears lemma for Petrov-Galerkin method. So Strang's first lemma deals with the situations like quadrature and isoparametric elements. We have, as usual, the energy space X and the finite element space XH that is part of the energy space X, and we also have the finite element test space YH that is part of the continuous test space Y. We have the usual bilinear form A and the discrete bilinear form AH, which is not necessarily equal to the continuous bilinear form A, that is only defined on the discrete space XH and YH. We also have the approximate right-hand side FH that is only defined for elements from YH, and of course the exact right-hand side F in the dual of Y. We denote the exact solution by X star, which satisfies the usual variational equation, and we denote the discrete solution by XH, which is the Petrov-Galerkin solution that satisfies this discrete equation, with, of course, the approximate bilinear form AH and the approximate right-hand side FH. Then the lemma says that the error of the Petrov-Galerkin solution, which is the difference between the exact solution X star and discrete solution XH in the X norm, is bounded by the sum of 3 terms. The first term is the usual term that comes in Sears lemma, and the other 2 terms are called consistency terms, which take into account the fact that the bilinear form AH and the right-hand side FH are not necessarily equal to their continuous counterparts. So the first term, the series lemma term, it has the usual structure. It has a constant that depends on the continuity constant of the continuous bilinear form A and the inf constant of the discrete bilinear form AH, multiplied by the exact solution X star minus an arbitrary element of the finite element space XH. So that means there is an infimum in front actually over the finite element space XH. The second term has this structure, which is the difference between the two bilinear forms, approximate and exact, applied to the arbitrary element X from the finite element space XH and Y from the finite element test space YH and taken supremum over Y. And note that this X here is the same as X here. So if we have the infimum over X here, that should be over the combination of these two terms. And the third term is consistency of the right-hand side, which is just the norm of FH minus F in the dual space of YH. As noted before, alpha H is the inf constant of the discrete bilinear form AH. The proof is not very hard, it's actually very straightforward. You pick an arbitrary element from the finite element space, then this difference is in the finite element space, this difference. So by the inf condition for the discrete bilinear form AH, we will have this inequality. Now that means we will need to bound that. So let's write that bilinear form applied to XH minus X and Y. So we want to have a X star minus X here, so let's just write that, and then this is just a negative of what we have here. Then this AH is what we had originally, and then we write AXY, so that comes from this part here, minus AHXY, that comes from this part here. Then we use the fact that AHXHY is actually FHY from the discrete Galerkin equation, and AX star Y is actually equal to Fy from the exact equation. So once you write this way, you will see that these last four terms immediately give us the consistency terms in the estimate. And the first term here, simply by boundedness of this bilinear form A, this is the norm of A times the norm of X star minus X. X is an arbitrary element of the finite element space, and the norm of Y. We want to bound the error of the discrete solution, so that's X star minus XH. That is bounded by X star minus X plus X minus XH. And X minus XH here can be bounded by these terms here, divided by Y and taken supremum over Y. The first term has X star minus X times A and divided by alpha H. So that gives us 1 plus that constant times X star minus X. So this 1 coming from that term here. And then we have the supremum over those four terms. So that's the first Strang lemma. Now, the second Strang lemma takes care of the situation with non-conforming methods. In this case, we don't even need to consider the exact equation. What we have is the energy space X, where the solution is in. We have the finite element spaces XH and YH, and we need this approximate bilinear form AH to be defined on X plus XH cross YH. So this is the space of elements of the form X plus Y, where X is from capital X and Y is from XH. We need this to be bounded, and we require that X plus XH has some norm denoted by this, and YH also has norm that is also denoted by the same notation. And we consider that there is an element X star in X which represents the exact solution, but in this lemma we don't need to look at the equation itself. So we just need one element X star, and we need an approximate right-hand side FH, and we need this discrete equation, the discrete solution XH satisfying this discrete equation. Then the lemma says that the error between X star and XH in this H norm, so remember this X star is in X and this is in XH, so the difference will be in x plus xh, and we're measuring that norm in this h-dependent norm, is bounded by the similar constant here. What is different here is that this norm of a that was in the Strang's first lemma is replaced by the norm of ah. There is no a actually in this lemma. That is multiplied by the error between x star and x. X is an arbitrary element from the finite element space, so there is actually an infimum over x here. Then we have this consistency term. In the consistency term, we get difference between fh applied to y and ah applied to x star y. This accounts for the fact that fh is not f and ah is not a. Alpha h is the input constant of ah, and these are the norms on x plus xh and yh. The proof is again straightforward. First, we take an arbitrary element from the finite element space and use that we have the input condition on the discrete space. Then we're going to bound that bilinear term. So this bilinear term is here. We write this simply as first x star minus x, and here we have xh minus x star. So this minus x star and plus x star will cancel to give us xh minus x, that is here. Then we write this simply ah applied to xhy is equal to fhy. That is because xh satisfies the discrete Galerkin equation. And we write ah applied to x star y simply here. The first term is bounded by the boundedness of ah, so that gives us x star minus x. Of course, the norm is now the h-dependent norm. Then we use triangle inequality. So the error between x star and the discrete solution xh is bounded by x star minus x plus x minus xh, and x minus xh is bounded by this argument here. And again we have 1 plus that, so this constant coming from ah divided by alpha h, this 1 coming from the first term on the right hand side here, and we have x minus x, and there is the consistency term. In the next few lessons we're going to apply these two abstract lemmas to some concrete situations.